the last presentation that we're going to give, which is not necessarily the last step in your analysis, because there's always more that you can do with the data, is on statistical inference. And so what I will do is I will try to explain how we can do statistical inference in general. And I'm actually assuming that a lot of you will have had statistics during your formal education. But what I will focus on is what are the specific things for EEG and MEEG? And the first question to ask is why do we do statistics? And I would say we use statistics to deal with uncertainty, which is often due to variability over observations. So we've been looking at data. Data tends to be noisy, which means data tends to be variable. And if the data doesn't make sense, we have to resort to statistics. But statistics, the term statistics is used in very different contexts. So you can also ask, what different types of statistics do we have? So one of the questions where you would use the term statistics is how do large distributions of something behave? For example, if we toss a coin many times, then we would get a binomial distribution. Or very often we're assuming that things are normally distributed or are Poisson distributed. And this all refers to statistics. But this is not the type of statistics that I'll be focusing on. This is more like how can I describe or summarize a distribution? What I will say, and we have different metrics for that, such as the mean, the standard deviation, the variance, the kurtosis. The type of statistics that I want to focus on this afternoon is how to make a decision or how to draw a conclusion. And that's where inferential statistics comes in. So this is all about inferential statistics. It's all about hypothesis testing. Inference is the process of drawing a conclusion on the basis of evidence and on the basis of reasoning. So we often have an hypothesis, we have an idea, and then we go into the lab and we acquire data, and we hope that this data is going to provide evidence in favor for our hypothesis. And there's two important approaches that people are taking. There's the frequentist approach, where we compute, and I think that's the one that is mostly formally taught, especially in the past. It's about computing p-values. And that's where we compute the likelihood of observing the data given one hypothesis, given the null hypothesis. We don't only phrase the null hypothesis, we also phrase an alternative hypothesis. And if we compute a p-value that is very small, then we would reject the null hypothesis in favor for the alternative hypothesis. But the thing is, we're always computing the p-value under the null hypothesis. The Bayesian approach is different. In the Bayesian approach, we compute the likelihood for multiple hypotheses. And then we compare the likelihoods. And then if there's really compelling evidence in favor for one versus the other, then we would favor the one that is the most likely. In a way, there's also still some thresholding involved there, and you might come up with the same conclusion. But the approach that is taken is very different in Bayesian statistics. I must say I'm more of a frequentist. That's how I was trained, and most of them, actually all of the method that I'm going to show this afternoon, have this frequentist approach. So computing probabilities given a null hypothesis. In inferential parametric statistics, like the normal type of statistics that we've all been taught, we make observations and we want to find out whether some hypothesis holds. And that's usually it's the alternative hypothesis. For example, we want to know whether men are taller than women. So we gather data and then we compute from that data, we compute parameters, the mean, the standard deviation. And on the basis of those parameters, we can make a decision. And the decision-making process is based on computing the probability, this p-value, of a value that we derive from these parameters, such as the t, under the null hypothesis. And this is the computation of the t. It basically takes in the mean, the observed mean, the expected mean, and then divided by the standard error mean. If the observed t-value that we can compute from our parameters is sufficiently unlikely, then we reject the null hypothesis in favor of the alternative hypothesis. The important thing is it's a parametric statistic. So what we're saying is if men are taller than women, we mean that the mean value of the length of man is larger than the mean value of the length of women. So there's a hypothesis about a parameter, which is the mean. It doesn't mean, sorry, it's a little bit confusing, but it doesn't mean. Perhaps I should have used average. It doesn't mean that the average height of man, if the average height of man is larger than the average height of women, it doesn't mean that every man is taller than a woman. It's just about the means, and that's the parameter that we're computing. Of course, this is also something that we can do for two conditions, and that's very often what we do with each, with MEEG analysis. We have a carefully designed experiment task where we have observations in condition 1, we have observations in condition 2, then we ask the question, are these two distributions, are they different? And again, we can compute a t-statistic, and based on that t-statistic, we basically follow the same procedure. So we make observations and we want to know whether some hypothesis is true by means of rejecting the null hypothesis. And the first problem with this is that it requires a known distribution of the test statistic. Very often we are assuming that our data is normally distributed, but that does not necessarily have to be the case. So the data can be skewed, it can have different tails. And that causes problems because we have like too many values on this side, we have too little values on this side. The second problem that we have, and this is like really a situation that we often have with these numbers that we're computing on the basis of EEG and MEEG. For example, power. Power is not normally distributed. Power is always positive. It actually has a very skewed distribution. If we log transform it, it gets a little bit more normal, but it's still not normally distributed. The same goes for source reconstructed activity. So there's or connectivity measure. So there's a lot of measures that we're computing from our EEG and MEEG data that are not normally distributed. The second problem that we have with parametric statistical testing is that of multiple comparisons. So yesterday we looked at time frequency analysis, and this is a very low resolution figure, sorry for that. What it shows along the horizontal axis is time, along the vertical axis is frequency. But what we've actually done is we've computed using this wavelet transform or another method, we've computed the value of the power at many different time points and at many different frequencies. So in total, if we were to ask the question, is there a difference? We're asking that question 480 times in this specific example. The problem is that if we do a t-test with an alpha, with a critical threshold of 5%, which is the chance of a false alarm, that's the critical threshold for one test. But we're doing 480 tests. And that means that if we were to do this on this data, so 480 times, then we have a 99.99% chance of at least one false alarm. And actually what we would expect, that if you just look at the false alarms, from this 480 comparisons, we expect 5% to be false alarms. So out of this matrix of values, we expect 24 false alarms. And that's problematic because we do want to make the right decisions. We do want to control for the family-wise error rate. So this is the multiple comparison problem. I'm sure you've all heard about it. For whole brain analysis, like the data set that we are working with, 306 channels, that's excluding the EEG channels, we easily have like 100 time points, 50 frequencies, like we will do like millions of statistical tests, which means that we'll have tens of thousands of false alarms. That doesn't necessarily mean that this is really the number that we're going to get, because all of these data points have some dependence on each other. It's not totally independent tests, but at least we know that the false alarm rate is not 5% as we would like it to be, but it's way larger. And that of course causes us to claim significance if it's just noise. So we have different solutions to control the family-wise error rate, and I'll just quickly show it from the future perspective, but the other toolboxes have exactly the same solutions. We have Bonferroni correction. In Bonferroni correction, we just divide the threshold by the number of tests that we're going to do. Okay, imagine dividing your 5% threshold by 1.5 million. You're not going to get anything significant anymore. So the Bonferroni correction, although it's a valid correction, it's a correction that is extremely conservative. We also have the false discovery rate. The false discovery rate does it in a different way. And we have, that's where I will mainly focus on, we can use a Monte Carlo approximation of the randomization distribution of the maximum statistic. And there's a lot of things within one sentence, but that is what I'm going to explain in the next few slides. Just very quickly to show how this works. So we have FT time log statistics. In FT time log statistics, you can put your grand average ERP data structure, and you can specify that you want to do a Bonferroni correction. You can specify that you want to do a false discovery rate correction, or you can specify that you want to do a Monte Carlo correction, where we're going to use the randomization distribution of a Monte Carlo. And we have the same function for frequency data. We have the same function for source level data. The other toolboxes have the similar mechanisms. So what I want to focus on next is on non-parametric randomization tests. And I know that sometimes it's confusing because we're using different terms. And I'm also using different terms myself. So sometimes we call this a randomization test. Sometimes we call it a permutation test. Sometimes we refer to this as Monte Carlo sampling. But in fact, we all refer to the same thing. It would be like a real randomization test if we would take our recorded data and we would have the trigger channel. And it would, for example, like over subjects, you would often like randomize your triggers, right? You would randomize your conditions. So imagine taking your recording and then replacing the trigger channel with that of another subject. And then what you have done is you've basically randomized the condition of the presentation of the trials. What we often do instead is, rather than taking this all the way to the level of the stimulus presentation, is that we're taking one subject's data and we're not randomly reassigning, but we're shuffling between conditions. And that's what permutation comes in. Permutation basically means replacing two items for each other. The Monte Carlo sampling comes in is that often we have so many possible ways that we can shuffle, is that it's not possible to exhaustively go through all of them. So rather than exhaustively going through all possible permutations, what we do is we take a random subset of the possible permutations, and that's where Monte Carlo sampling comes in. So that is why these three terms are often used together. The strategy that we're using is that the randomization approach allows us to compute the likelihood of a hypothesis that is not about a specific parameter. But as a disclaimer, we will still use some parameters in these computations. So we're doing a non-parametric test, but we're still going to compute some numbers, and these numbers are parameters. The general principle of a randomization test is that we have an independent variable, which is basically our stimulus presentation. It's the sequence in which we've presented these phases in this experiment. And then we have a variable that might or might not depend on the independent variable. So there's one variable that we control, it's the sequence of stimuli, and there's one variable that might or might not depend on that, which is the brain data. What we say in a randomization test is that the data is independent from the condition in which that data was observed. And you can basically rephrase that the data, and if we have two conditions, you can rephrase that saying that the data does not depend in the condition in which the data was observed. Or you could say the data in the two conditions is not different, is not different, like it's the same. It's not exactly the same, but it comes from the same distribution. And this is an approach that we published in 2007. It's so the paper has all the mathematical details behind this. Now, what I'm going to do next, I'm just going to give a very intuitive explanation how we're making use of the randomization test to come up with a cluster-based permutation test. So the idea is we have data in condition A, data in condition B. We can do some sort of analysis on it. And then given these two analyses on these two different data sets or these two different conditions, we can compute some difference. Let's call that difference our original difference. The computation that we do can be anything. For example, it can be computing the mean and the variance of the standard deviation. And if we have the mean and the standard deviations, we can take the means and the standard deviation, and we can compute a t-score. So the number that we compute can be a t-score. However, what we do is we don't have an hypothesis about the t-score. We have an hypothesis about this data. And the hypothesis is that the data can be shuffled. So what we do is we shuffle the data and we recompute the statistic. And we shuffle the data again. And actually, we shuffle the data many, many times. And every time we're computing this statistic. And that is going to give us a randomization distribution of this statistic. And it does not matter what we're doing in between. As long as we compute some number, it's fine. Because the hypothesis is not about this black box. The hypothesis is about me shuffling the labels of the two conditions. What this results is that because we're shuffling many times, so this results in a distribution of the number that we're computing. It results in a distribution of these numbers. And that distribution can take any shape. It can be nicely normal, it can be skewed, but it can basically, I don't really care how it is shaped. The only thing that I care about is where does the original number that I computed, where does it fall relative to this distribution? If the original number that I computed, if it falls in one of the tails of this distribution, I would consider that very unlikely. That's actually also what we're doing with a regular test, computing a t-value. If the t-value is very far in the tails of the t-distribution, would also say that's very unlikely. But here I've computed this distribution on the basis of the data and on the basis of the resampling. So in non-parametric statistics, we randomize the relationship between the data and the independent variable, the condition. The hypothesis that we state is one about the data. It's not one about a specific parameter. So the null hypothesis, the data is independent of the condition and therefore it can be shuffled, and the alternative hypothesis that the data does depend on the condition and it cannot be shuffled. And then the distribution of the statistic of interest, which I call X here, is approximated using a Monte Carlo sampling approach, so using random sampling. And then what we do is we estimate the likelihood of the null hypothesis by comparing our observed statistic relative to the randomization distribution. And it's that simple. Okay. What I said, so as such, I have not done anything yet that is necessarily beneficial. One thing that is beneficial is that here I'm not making assumptions on normality of the data. But we also identified other problems such as the multiple comparison problem. So let's see how we can deal with the multiple comparison problem using this approach. I said we can use anything in this black box. So the statistic can be anything. And rather than computing a statistic for all our channel time frequency points, what we can do is we can put all of the channels and times and frequencies in the black box, and only the maximum channel time frequency point comes out. So we can take the most extreme observation and use that for our statistic. So what we do is, rather than computing the randomization distribution for each channel time frequency point, is we're computing the randomization distribution for the most extreme statistic over all of those 480 points. That's going to give us a distribution. It's going to be a weird distribution, like one that is not directly predictable, because like, what's the distribution of the maximum? But I don't care. The only thing that I care about is, like, where does my observed maximum lie relative to this distribution? Small caveat here is that we often compare two extrema, one for every tail. So we often, if we don't have a clear hypothesis of whether there's a positive effect or a negative effect, we would do this for both tails, and we would compute distribution for the maximum, for the most positive statistic, and we would compute a distribution for the minimum, for the most negative. And then we still use Bonferroni correction to deal with those two distributions. All right, so that is one thing that we can achieve, that the non-parametric test framework allows us to do. We can use an arbitrary statistic. Another thing that we already identified is that if we do a Bonferroni correction, our alpha has to be adjusted greatly. That greatly reduces the sensitivity. And since we have many time channel frequency points, that's definitely a challenge. So if we do conventional univariate parametric statistics, so univariate means that we repeat it for every variable that we have observed, so every channel time frequency point, then we have this massive multiple comparison problem. But our approach here is to consider the data. We have many channels, time points, frequencies. It's massive univariates, and we have this multiple comparison problem. But there is quite some structure in the data. And it's a structure in the data that we can exploit. Channel time frequency points are not independent. Like if we have an ERP component, and if we have sampled fast enough, then the next sample is still going to show the same component. Or if we have frequency resolved data, then among other due to spectral leakage, but also just due to the characteristic of the signal, these frequency peaks are not extremely sharp, unless perhaps the 50 hertz, but like alpha, that's a broad bump. And that is something that we can exploit. Because neighboring channels will also see the same, like we'll largely see the same sources. So neighboring channels, time and frequency points are expected to show similar behavior. And that means that we can combine neighboring samples into clusters. So what we're doing is we're accumulating the evidence by looking at the neighbors. And that's where cluster-based statistics comes in. And like in the previous slides already showed how we deal with multiple comparison problem, and that stays the same. So what we do is we avoid the multiple comparison problem by comparing the largest observed cluster versus the randomization distribution of the largest clusters. So one is to avoid multiple comparisons, and the other is to increase sensitivity. So let's look at how this works in a real data, in a data set. So this is subject 01. It's one of these tutorial data sets that we use a lot on the YouTube tutorials. It's not the one that we've been using here. It's a language experiment in which sentences were presented in which one word was congruent or incongruent relative to the preceding sentence. And for those of you familiar with language, you know that's going to elicit an N400 component. So this is the average this is the average over time amplitude. So this is the MEEG measurement, so it's in Tesla or in Tesla. And this is this N400 effect. So this is the average overall file. Of course, we have this measured on each individual file. What we can do is we can compute average, but also the standard error mean. And then we can set thresholds. And then normally what we do is we would set a threshold. If you have a lot of files, it would be 1.96 for the p-value. So it's about 2. And then we can look at where is the data. So this is now plotting the t-statistic. So it's plotting the statistical contrast between these two. We can look at where is the data larger than 2. Well, it's here, it's here, it's here, it's here, it's here. So there's many data points, many time points at which the statistic exceeds our thresholds. But that's what we would also have to do, like a Bonferroni correction. So if you Bonferroni correct for the number of time points that we have, the threshold needs to be adjusted, and the threshold becomes 4 in this specific example. And then there's still one time window in which the t-value exceeds the threshold. Right, so that means that uncorrected, these would all be these will be the time points or the time windows in which the t-values exceed the threshold. Bonferroni corrected, this would be the time window in which the data exceeds the threshold. If we do a cluster-based, I will explain in the next slides how that's going to work. Then this is one large cluster for which the probability is so unlikely that we would say there's a significant difference between the two conditions. This is something that we can do in time. And actually here I've cheated quite a bit because I've already selected a channel where I know that I'm going to have an effect. So actually this is p happening. If we look in time frequency, we would have less expectations in terms of time frequency. We can do the same approach. Here you see the original the difference in time frequency between the two, between the congruent and incongruent condition. This is if we do a test without correcting for multiple comparisons. The test, if we do a correction for multiple comparisons using Bonferroni, is not shown because then nothing is significant. This is the result that we get if we use a cluster-based permutation test. And what you can see here, that there is one cluster corresponding to the largest cluster that we have. And this can then even be further extended, so we can also include channels. And if we include channels, then this is the contrast between the two conditions. And then we have a cluster which both has spatial extent, but it also has temporal extent. And it also has spectral extent, so the spectral is very difficult to plot. But there's a cluster in time frequency and space that is so unlikely that on basis of that we would say this data is not the same in the two conditions. Let me explain how this works in a slightly more detail. So what we have is for each of the participants, we have a data matrix. And so that could, for example, be an ERP. And we have the data matrix for subject 1 in condition A, we have the data matrix for subject 1 in condition B. And we have that for, let's say, 10 subjects each. The null hypothesis states that the data in the conditions is not different. So that means that we can shuffle. So what we do is we shuffle randomly between the two columns. And of course, the data might depend on the subject. So we're only going to shuffle within a subject. We're not going to shuffle randomly, like not totally randomly. And every time that we shuffle, we can compute a statistic over all of these numbers, which is usually done by taking the difference and then computing the mean and the variance and then computing the t-square. In this case, it's data that is measured over all channels. So that means that our original observation might have a cluster both in time and in space, possibly in time, frequency, and in space. And then what we do is we look in time, frequency, and space for channels and time points, like neighboring channels and neighboring time points that are connected and that exceed a certain threshold. And that's what we call clusters. So here you see 1, 2, 3, 4, 5, 6, 7 clusters. And we take the largest one, and that's the one that we're going to write down as the original observation. Then we're going to shuffle. And every time we shuffle, we're going to find a cluster, and we're just going to write down all of those permutations. This list of numbers gives us the randomization distribution against which we can compare the original one. So if we then look at how this works, we have estimated our randomization distribution with the size of the largest cluster, and we can look at how the size of our original largest cluster compares to that. If it's very unlikely given the randomization distribution, we reject the null hypothesis of the data coming from the same distribution. So to summarize the channel level statistics, we have a parametric. We can make a parametric statistical test for all the channel time frequency points. That means that we try to compute the probability for the null hypothesis, but we have one null hypothesis for each channel time frequency point, and that gives us a multiple comparison problem. Or we can use this non-parametric approach for estimating the probability, where we use a randomization or permutation approach to estimate the randomization or permutation distribution. And that allows us to compute the probability of the null hypothesis for an arbitrary statistic, which allows us to avoid the multiple comparison problem using the maximum. And it also allows us to incorporate prior knowledge from the structure in the data to increase the sensitivity. Okay, so this is like an important point that I want to make sure that everyone of you grasps. So that's why I've inserted questions like that. So are there any questions at this moment? Let's just wait for the microphone. Sorry, I should have told you that there were questions coming.
Sometimes when you do this cluster-based permutation tests,
Can you speak in the microphone a little bit better?
yes, yeah. Sometimes when you compute these cluster-based permutation tests, you have several clusters that are coming out. So I was wondering, when you explain here, you say you take the biggest cluster, the maximum clusters, but how do you do for these other clusters, and when do you decide whether they're going to come into this second level of computing the distribution?
I have more slides to come, so this is going to be covered in one of those slides. I'm just going to postpone down to this. But it is very good. Any other questions at this moment? No, then I'm going to move on, because there's a lot of nitty-gritty details that you should also be aware of. So on the train here, Britt and I were discussing also what should we present, and we came up with a list of things that we often have as questions, like how to interpret the outcome, how to deal with randomization tests for source data. So far, I've only explained channel level data. How to deal with, and that this was like a little bit based on the discussions that we've had in the hands-on session with some of our participants. Like we had a question like how to deal with data that has a bias. For example, if you have many more trials in one condition than in the other. How to test parametric effects, how to test a single condition, and how to choose the threshold. I hope that I can explain each of these so that you become confident. So first of all, how to interpret the outcome. There's no cluster. So in your case, you say, well, there's two clusters. You should not necessarily think about these clusters, because there are clusters, but these clusters are not necessarily things that we should be interpreting. the probability that we compute tells us that the null hypothesis is unlikely. And the null hypothesis is not about the cluster. The null hypothesis is about the data. So the decision that we make if we have a cluster that is very unlikely is that the data is different. If we then look at where do these clusters come from? So for example, this is like a toy topography of a dipole with a slight orientation difference over the participants. And the way that the dipole projects onto the scalp results in a slightly larger positive topography on one side and a slightly smaller negative one. If this varies over subjects, what we're going to see is that the red blob is going to be a significant cluster, and the blue blob is going to be a cluster that might or might not be significant. But it's not the cluster that is significant. It's the brain activity that generates the data that is different. And if we would observe such a pattern, we should not be interpreting it as the source being activated, the source being located here. And that's also not what you would do if you would see this ERP. You would recognize the dipolar pattern. You will know that the source is in between. So you should not interpret the cluster, but you should interpret the data. So in this example, only the positive cluster will show up as significant. Just another example. Imagine that we have a difference in the latency of an ERP component, like relating to the talk that I gave yesterday. If that is the case, and if you just imagine this being noisy over all the trials or all over all the subjects, what's going to happen is that only the steep flanks will show up as significant. So this difference over here, that's going to be significant because that's a large difference. Like vertically, that's a large difference. Whether the difference here is going to be significant, well, I don't know. It depends on how noisy the data is, because the difference is smaller. Like vertically, the distance is smaller. So what would happen here is that I would get one or two clusters. I would definitely get a cluster over here. I might get a cluster over here. But that does not necessarily mean that I should be deciding that there's difference in brain. Well, of course, it depends on how you see it. You should not focus on the cluster and saying the difference in activity is here. Because what you should probably is like a more appropriate explanation is that you would say the component is later. And due to the steepness of the flanks of the component, I'm seeing a cluster at the start, and I might see a cluster at the end. The inferential statistics for which the parametric test helps is about the decision making. And after the decision that there is a significant effect, you still have to do the interpretation. And the cluster often guides our eyes towards a feature in the data that is often relevant, but it's not a cluster that you should interpret. You should use the understanding of the data, the recording system, the analysis methods, the potential compound, and all of those things should go into the interpretation of the data. But it's after having made a decision that the data is different, then you're able to make the interpretation of the data, which is also one of the reasons that we often do statistical comparison at the channel level, because that reduces our search space for the source reconstruction. So if we do time frequency analysis, and if we in a time frequency analysis, we find a significant difference between the conditions, so the data cannot be exchanged, then the cluster is going to tell us where in the data the difference is. And that is where we would also have the follow-up question, like where in the brain is that difference? So that's why we're also using that strategy. If we see it if it's significant on the channel level, then it must be significant at the source level, because these channels are recording the source. So we don't have to do the statistical test again at the source level, because we already know that it's significant, or we already know that the data is not exchangeable. Does that answer your question? Not sure. Yeah. I think it's really the cluster, like the cluster can guide you towards the part of the data where the difference is large, because that's also how we compute the cluster. The thing that we put in the black box, we try to make it such that it emphasizes the largest difference.
Not interesting.
Okay, so that answered the question. So that's good. Okay. I've just said that we that we often do a randomization test at the channel level because it reduces the search space for source reconstruction. But you don't have to do a randomization test at the channel level. You can also do it at the source level. And sometimes it's more statistically more sensitive to do it at the source level. Let me just explain how we're doing that. So again, if we think about inferential statistics, we have numbers that we're estimating. We can think about these distributions, and we computed the t-value. In the case of source level data, each of these observations is, for example, the source reconstructed activity of one subject in one condition. So each of these, for example, you can think of it as a volume, like an fMRI type of thing. And what I'm going to do in the next slides, I'm going to show it as if it's a vector. So I'm just going to squeeze it out. The number of voxels is still the same, but this just makes the plotting a little bit easier. So what I have is data that is observed in one condition, where each of the columns of this large data matrix is one observation in one participant. And I have the data observed in another condition. And what we can do very easily, we can compute the difference. We can compute the mean value of the difference, standard deviation of the difference. That gives us a vector of t-values. For every voxel, we have a t-value. Under the null hypothesis, the data between the two conditions can be shuffled. So that's what we're going to do. And this is something that we can do many, many times. And every time we can compute this vector with all the t-values. And then, of course, what we want to get at this distribution. So again, if we look at what we're doing, so this vector of t-values, we can reshape it back into its original volume. We could set a threshold. We can cluster neighboring voxels for which the t-value exceeds the threshold. And what we normally do is we compute the sum over the cluster. And it's the sum of the largest, or its largest cluster is usually the sum of the largest cluster that we use in constructing this randomization distribution. Okay, so far so good, but this is not exactly how we're doing it, because we know that from the null hypothesis that the data in two conditions is actually the same, or is not, it can be exchanged. So that means that if we want to improve the quality of our source reconstruction, rather than using one condition, we can take all of the data. And I think I should have not started with subject level statistics, but with single subject level statistics, where each of the columns is not a subject, but each of the columns is a trial. So imagine you having single trial data, and then imagine computing single trial covariances. Those are going to get very noisy single trial source reconstruction. But under the assumption that the data comes from the same distribution, we can compute the covariance over all the trials. And that's where common filters come in. So this morning, Britta gave an excellent explanation on how beamformers work. And I'm just gonna, so this is my only slide that has some math on it. I will try to talk you through it. If you don't really understand, it's also fine. So what we have is we have the measurement, which is the gain matrix, or which is also called a lead field, times the source time series plus noise. What we want to do is we want to get the source activity given a measurement. And for that, we multiply the measurement with an inverse weighing function. So these are the spatial filters that we compute with a beamformer, for example. But it's also the spatial filter that we can compute with a minimum norm. In the case of a beamformer, this is the way that the spatial filters can be computed. They depend on the lead field, they depend on the data covariance matrix, and we just toss them all in this equation, and it gives us the spatial filters. Okay. This depends on the data covariance matrix, and the data covariance matrix can be computed by multiplying the measurement with the measurement transpose and then dividing by the number of samples. So this morning we've looked at the data covariance matrix in the source reconstruction. And if we use this, we can also compute the power. So this morning for filter, we did not compute power, we looked at time series. But the power can be computed from the estimated time series of the source times the transpose of the estimated time series divided by the number of samples. But we can also, like if we just see where this x comes from, we can take these ones and we see that this one actually simplifies to this one, because we can take this, we can put it in there. So we can take this, we can put it in there, and we get this one, and that gives it up. So the power is basically, it's the spatial filter It's the data covariance matrix sandwiched between the spatial filter. The trick that we now use is that we can say, well, we can estimate the data covariance matrix on the single trial. But we can also estimate the average data covariance matrix. And it's the average data covariance matrix, which is the covariance matrix over all the trials averaged, that goes into the computation as filter. So for all the trials, we have the same filter. But then what we can do is using that filter, using this filter, we can compute the power for each trial individually. And that gives us an estimate of single trial power, which is not extremely noisy, not extremely blurry. It's still not going to be very sharp, but it's a much better estimate because we have a much better estimate of the noise that needs to be suppressed, and we have a much better estimate of the structure in the data. So that means that under the assumption that the data comes from the same distribution, the optimal filter that we compute is one that is based on the average covariance matrix. And it's with that one, we can very efficiently, we can compute the power or the variance for each of the sources for each of the trials, and then we can shuffle. Okay, it was this is difficult, but let's take a deep breath. I also put this in there like as a reminder that I shouldn't simply barge on. Any questions? You're still good? Yeah? Okay. Then I'm just going to continue. And then there will be time for questions afterwards as well. Another thing that we addressed, that like two of my participants like already asked me about, like how should they deal with data that is biased? For example, you have an experimental design that by definition, like a go, no-go task, or a standard and a deviant, like an oddball task. In one condition, you have 80 trials, in the other condition, you have 20 trials. That if you would not deal with that in a particular way, if you just say, I'm going to source reconstruct the 80 trials, I'm going to source reconstruct the 20 trials, that's going to result in a very sharp and very localized source reconstruction condition 1. And since the 20 trials will have a much less signal quality, like more noise, it's going to result in a more blurry source reconstruction in condition 2. If you do like a naive comparison between these, you might conclude that there's a difference between, because the source reconstruction in condition 1 is more sharp and probably has a higher peak at the location of the source. But what you're doing is you're not comparing the activity, you're comparing the noise, which is larger in condition 2 than it is in condition 1. Second problem that we're not touching upon in these days is about connectivity estimates. Let's say that we estimate coherence. Coherence is a measure of phase consistency. In condition 1, because we have more trials, we will have a lower, because it's going to be a less biased coherence. Coherence on one trial is always 1. Coherence in two trials is still pretty large. The more trials you have, the more accurately your coherence is going to close to real coherence. So if you have fewer trials, your coherence is going to be larger, trivial. The way that we can do statistical tests with data that follows these patterns is by considering that we have like data in condition A, we have data in condition B. And what we do is that we shuffle the data between the two conditions in such a way that the size of both of the conditions stays the same. So we can basically take a sum of these, we can put them there, we can take these ones, put them there. But we're going to shuffle them such that condition 2 always remains the smaller condition. And if we then compute the difference between the condition, then that difference between the conditions for each shuffle is also going to include this bias. That means that we're going to estimate a randomization distribution, like a biased randomization distribution, and we're going to compare our observed biased measure relative to this randomized, the biased randomization distribution. And that's a method that also that my colleagues have published about specifically for coherence difference, but the approach basically holds for anything that is biased. Yeah? Okay. A question that we often get is how to test for parametric effects. A non-parametric test is not about the parameter. but we have many experimental designs in which we actually make the experimental design such that we have a parametric effect. So testing for differences between faces versus scrambled, that's easy. We'll just shuffle between these two. Or here we can shuffle between the unfamiliar and the familiar, or between the first and the second presentation. But what if we have a question about whether the first and the second presentation, whether they're different for the unfamiliar and the familiar faces? So that's what we, using conventional statistical methods, would use an ANOVA, and an ANOVA is like based on the GLM. And what we're doing with an ANOVA, if we want to test for the interaction effect, we're first estimating the main effects. So the main effect of the familiarity, and then we have the main effects for first versus second presentation. And then the interaction effect is actually testing whether on top of those two linear main effects, we still have something that cannot be explained by the GLM. That's what the interaction term comes in. The trick that we use here is that we compute the difference between the two conditions. So we take the second presentation of the face minus the first presentation, and then we use the condition difference instead of the original data. So if you take this data, we're going to take these 100 files, we're going to subtract these 100 files. We like that's something we usually do at the group level. And the same here. So that means that we have 100 differences here and we have 100 differences here. And if I have 100 numbers and 100 numbers, I can again start shuffling. So rather than testing it on the original files, I'm doing the test on the differences. And then the hypothesis that I'm stating is that the differences can be shuffled or the difference cannot be shuffled. If the differences cannot be shuffled, then the differences must be different, which means that there's an interaction effect. The same logic also applies if we have, for example, a parametric experimental design where we have like some continuous variable that we hypothesize to relate to brain response. So we can estimate the regression beta coefficient and we can shuffle that between conditions. So you don't have to do the shuffling on the raw data. You can do the shuffling on something that you have computed, and then that's basically your inference shifts to that level. Another thing, like so far I've always been saying that I'm using a permutation test. So I'm shuffling between two conditions. So what I'm doing is I'm doing something like this. But what if I don't have a second condition? So what if I want to test data that I only have a single condition? Like, what if I want to test the visually evoked potential? So what we normally would do is we would do a one sample t-test where we would compare the amplitude, the average amplitude of the visually evoked potential relative to 0. And that's also what we can do here. So what we can do is we can take a pseudo data set, we can make dummy data that has zeros, and we can shuffle. What we're basically doing is we're creating a dummy data set in an unobserved condition where we replace the real numbers with zeros. And if you just think about it, let me just go back. If you just think about what this means, that I'm computing the mean value of this minus the mean value of this, what I'm effectively doing, I'm flipping the sign. Every time that I flip this one over, I'm basically doing 0 minus this one. So I'm flipping the sign of my individual observation. So testing a single condition can be done by sign flipping of the original data, which is also one of these strategies that's not only implemented in FieldSub, but I know the Python also has it, right? So AEG Lab also has, so I'm not sure about brains, but I guess it also has. The hypothesis then becomes a little bit different because we cannot say that the data is the same between the two conditions. But what we're saying is that the data can be swapped with 0. Or alternatively, you could say the sign of the data can be swapped. Under the null hypothesis, the sign of the data can be swapped. So under the null hypothesis, you could say the data is symmetric around 0. And if the null hypothesis is very unlikely, well, then the data is apparently not symmetric around 0, which means that it must be on one side of 0, which means that it's different from 0. That the mean value is different from 0. Okay. One final question I often get asked is like how to choose the threshold. There are two thresholds involved. There's one threshold that is involved with clustering, because we first have to set a threshold to see where the number that we have computed exceeds that threshold, and that's what we use for the clustering. And then there's another threshold, which we call the alpha. That's for the decision making. The threshold for the decision making, that's what we like commonly have agreed upon to set that at 5%. So that's not one to play with, unless you have really good reasons to change that. But that's like more of a joint agreement. But the threshold for the cluster forming, that is one that's actually a parameter that you can tweak. Here, if you imagine, again, the ERP data. So we have the ERP data, we have the T statistic. We could have chosen any other thresholds. If we do that, the validity of the test does not change. The validity of the test is about data being exchangeable, but the sensitivity of the test will depend on the threshold. If you set the threshold too low, so if we would set the threshold like somewhere over here, we would get very large clusters. And probably in each of the random shuffles, we would also get very large clusters. So the sensitivity of the test goes down. If we would put the threshold very high, like for example over here, then we'll get very small clusters, or we might not even get any clusters at all. If we don't have any clusters, we cannot make any inference. So you have to hit the sweet spot. And the sweet spot that in the future implementation that we've set as a default is that we set the cluster thresholds at the uncorrected 5% level of the parametric threshold. And that's also why in the earlier images that I showed, but also here, like the size of this cluster corresponds to the cluster that we would see if we were to set a threshold that is uncorrect. And I think this also relates a little bit to how can you interpret these clusters. So you know, if you use this default, you know that the cluster that you're going to find is that part of the data which exceeds the thresholds if it were not corrected for multiple comparisons. Okay, again, time to go deeper. I've gone over quite a lot of things. I've explained how to do descriptive versus inferential statistic. Inferential statistic is about the decision-making process. I've shortly touched upon parametric tests, like which is familiar to everyone. And I've explained how non-parametric tests are very different. And there are multiple non-parametric tests. The one that I've explained is a randomization test. And the hypothesis that we state is that the data is exchangeable or that it's not exchangeable. And if it's not exchangeable, then it depends on our experimental manipulation, and that's usually interesting. What I've explained is to avoid the multiple comparison problem by not testing every individual channel time frequency point or every individual voxel in the source reconstruction, but by taking the max statistic. And I've also explained that in order to increase the sensitivity, we use clustering. And we use those together, so we take the maximum cluster. Then in terms of the more advanced topics, I've touched upon how to interpret the outcome. Like this cluster, we should not call it the significant cluster. It's the test that is significant, but the cluster still guides us to that part of the data that we have to try to understand and explain. I've explained randomization tests for source data using a common filter approach, which is especially useful for beamforming, but also works for minimum norm estimates. I've explained randomization tests for data with a bias. And especially with the bias that there's more trials in one condition than in the other condition. I've explained how to test parametric effects, such as an interaction effect, which is based on an ANOVA, and it's a parameter, but you can just repeat the shuffling on that parameter. I've shown how to test a single condition by doing the sign flipping, and I've shortly touched upon the threshold. I think I should leave it at that. So with that, I would just open the room for questions. Thank you.
Thank you very much for your talk. I just have one question about defining the cluster.
Get the microphone up a little bit.
Or maybe like this? No?
Probably if you point it more to your mouth, it's already going to.
It's already there. So, so when you're defining the configuration for the test in field trip, I remember you also have to define what constitutes a neighboring data point. And I just wonder, based on what you decide, how many neighboring data points you need.
Yeah. That actually, let's quickly see whether I can. Where did it go? Yeah. So here I show this toy example. Normally our channels are not organized like this. So normally our channels are like, of course, you can say the channels are closer by or further away. In time, it is very obvious what the neighbors are, and frequency, it is very obvious what the neighbors are. In channel space, it's not. In some situations, it's actually even difficult to say whether channels are neighbors or not. For example, if you have intracranial recordings, then two channels that are relatively close by, because of the very focal nature of the intracranial recording, they would still pick up very different activity. So what you always can do is you can restrict the clustering to time and to frequency. You don't have to use clustering over channel. But of course, if your channels do pick up the same activity, then you have to tell on which channels you expect the same activity. So with EEG, we typically, and of course it also depends on the density of your EEG system, but with EEG, we typically would say like 4 or 5 channels around each of the channels. That's what we would define as the neighbors. And it's the neighbors that then, again, have their own neighbors, and then those neighbors again have own neighbors. With MEEG, the channel density is higher. But with MEEG, also the way that the radiometers are organized in the helmets is totally standardized. So for MEEG, we have standard neighbor structures. There are some MEEG systems for which we don't have a neighbor structure. Like for example, with the NeuroMax system, with the horizontal and the vertical planar gradients, that's actually a little bit weird, because the horizontal and the vertical planar gradient that are next to each other, they're not necessarily going to see the same force because of them being very focal. So we don't have a standard neighbor structure for the planar gradiometers of the NeuroMax system, but for the magnetometers, it's again clear. For EEG, we don't have standard templates because each EEG cap is different. And it's not very different. But if we make a neighbor structure for a high density cap, then I would, then like channel would have a neighbor that's close by. If you then take your EEG recording and that EEG recording would have fewer electrodes, then the neighbors will be broken. So that's why for each of the EEG caps that you're using, you would have to define your own neighborhood structure. And we have different strategies for that. You can make them on basis of a 3D electrode positions, on basis of a 2D template layout. But you can actually also hand code them. And I think what's an important thing to realize is that you only need to define the neighbors once per recording system or per electrode cap. It's not something that you have to repeat for each of your participants. Even though the caps would be slightly differently placed over the participants, you would still consider the same channels to be neighbors. So this is a one-time effort. Once you've done that, you can just use it over all your participants, and you can share it in your.
To the neighborhood matrix, right?
Yeah, it's the neighbor structure. Yeah.
But then in your configuration, you also have to define how many neighbors you need as a minimum to be.
Oh, that parameter. Yes. Yes. We do have some. If I go. If I go here, what we have is we can get very, very psychedelic patterns of neighbors. And that's because it's not only about whether things are neighboring in space, but also whether they're neighboring in time. And then through time, they can be, again, connected in space. So what we have observed that in some data sets, the clusters are getting too large, which reduces sensitivity. So so that's where the min NB this, min and D option stands for is the minimum number of neighbors that is required to connect two pieces of the data together. So with that is an option, and I never touch it. For me, usually the defaults work fine. But if you find that you don't have the sensitivity, whereas you have very large clusters, it might be that you're in the sensitivity range that I also explained with respect to the thresholding, that you're just getting too large clusters. And then this option helps you to break the clusters apart, thereby to be better positioned along this inverted U shape for the sensitivity. Yeah.
Yes, you talked about using this method for one condition, to test one condition. But what about, for example, three conditions? Do you have a way to adapt it?
So if you have like a factorial design with one level, three conditions,
Yeah.
then what you would do is you would compute an F-score.
Yes.
So that is something that you can put in the black box. So the number of conditions is actually not limited, but it's just shuffling between the conditions. It's the test statistic that you then have to change. We very often use a T statistic and two conditions, but you're not limited to that. Actually, you can make your own black box. So in filter, those are called stat funds, and we do have stat funds for an F test. And what you then would specify is that your data structure, either over participants or within a participant, that it has three levels, like 1, 2, and 3, and you would shuffle between the three.
Okay, so you shuffle between the three groups.
Yeah.
Okay.
Yeah. Of course, the thing that we're not doing this that often is that if you have an omnibus effect, which is what you would get if you would have three conditions, then usually you want to follow that up anyway with sequential individual tests. So as such, you could also decide to directly go to the individual test. But that's neat up to you.
Thanks for the talk. I have two questions. The first one is really basic. I was wondering how many items do you pick to be shuffled in each permutation test? Is it a random number or?
Yes. So actually, we really put all. It's basically drawing without replacement. So if you just imagine marbles into colors, we put all the marbles in one pot and we redistribute them over to condition. So it's really totally randomly, it's reshuffled. That doesn't remind me, like, how many reshuffles can you have? So I told that we often do a Monte Carlo sampling. So it's not really your question, but since we're talking about the shuffling anyway. I said we're often doing a Monte Carlo sampling because we have way too many shuffles. If you imagine two conditions, actually, if you imagine two conditions, so here I have 10 items on one side, I have 10 items on the other side, and for each of the items, it can be into position, like it can be original or swap. So that means that the total number of permutations that I can make here is 2 to the power of 10. So 2 to the power of 10, that is 1024. So I can make 1024 permutations, and actually half of them are not interesting because it's just like the whole thing swapped. So actually there's 512 interesting ones. With filter, we computed the 1024 anyway. So if you have 10 or 11 or 12 items, I would do config non-permutation is all, because then you really want to have an exhaustive list. If you get more than, let's say, 12, 13, or especially if you have 100 files and you want to shuffle those 100 files, then you just specify a number. And then the larger the number, the more accurate your estimation of the permutation distribution.
And the second question is, what do you think about methods that are based on classifier to discriminate two conditions compared to this statistical approach? Would it be like conservative the same way, or I don't know?
I don't think that classifiers are necessarily orthogonal to this approach. Like what we often do with classification methods is that we use cross-validation. cross-validation in a way is also like resampling the data, but it's like a more structured way of resampling the data. We're not necessarily shuffling between the conditions, but we're sampling the data, and we're splitting the data in train and in the test data set, and we might be repeating that multiple times with the resampling. The classification approach, of course, tells you like how accurate you can classify. It doesn't really give you this direct decision whether the data is different. So but of course and then you can say you can compute the likelihood of the classification, which for a two-class classifier is like a binomial distribution, and you can still make that decision. So I think a classifier can also be seen, like it can often be seen as a multivariate analysis, and this is also a multivariate analysis, because what we're doing is with these clusters, we're also combining the massive univariates into one cluster, and then we make one decision based on that. So our decision that there is a cluster can be considered as similar as the decision there is a class difference in the classifier. It's just that the way that we compute our probabilities is not based on a binomial distribution, but is based on some other statistic that we can make, where we have more flexibility than we have in the classifier. But the classifier, of course, is more flexible in the patterns that it can pick up, because we're making a very specific assumption that neighbor time, frequency, and channels, or neighboring source points, that they show the same effect. Whereas a classifier might, for example, be able to capitalize on different features in the data that are also like related to each other, such as, for example, the shift in the ERP that I showed, the rising flank and the falling flank. Classifier would probably be able to pick up on that and be able to classify on that quite well. So both of them are a very useful technique.
Thank you.
Any other questions?
Thank you very much, Robert. That was a great and very clear talk.
So this morning, with Britta over breakfast, we already identified there would be like also like a lot more for Britta to talk about in the forward and in the inverse modeling section. So we also like more or less agreed that if you still have questions about the source modeling, perhaps this would also be like a moment to address these. So Britta can also get back on stage, so that we still have some time on that as well.
Sure.
If that works with you.
Oh, yeah. Of
Yeah.
course, at the panel discussion, right?
No, we can also take the questions now, and then we can do the panel discussion more on the hands-on, like more, so that we now take a few questions on source modeling.
Sure.
If you're still up to it, Britta.
We'll try to keep it concise.
Oops.
If there is any.
Are there any questions about the source modeling, especially with relation to the hands-ons that we've respectively been doing with and the ideas that you might have on that?
Nice.
So maybe it's not exactly related to the morning stuff, but kind of. It's about atlases. I think we didn't talk about them that much, but we will, I guess. So my question is whether it's possible to convert from one atlas to another, in the sense that imagine in one atlas I want to look at something parietal, let's say, and it corresponds to some cloud of points, and then I ask which regions in another atlas these points correspond to. Is it possible even or not? Because I tried and it's like apparently very difficult.
Well, yes and no. So just as a background for people who might not know yet what an atlas is, an atlas is what we call a labeling of your source space. So you might be familiar with Broadman areas. That in the widest sense is an atlas because it gives a label to a specific region and source space. And there's many, many different ways of labeling your source space or your brain space like this. I know that both in FieldTrip and MNE, the way this would work is to go via one normalization. So in MNE Python this morning, we morphed our output to what we call the FS average space, which is a normalized brain space that you can morph an individual MRI into. And in those spaces is usually where we also would have the labels of an atlas attached to the different points on that MRI. And now you can, of course, go from this normalized average brain. In FieldTrip, it's often the MNI brain that you would use. You can go to one atlas or to another. So you wouldn't really go between atlas A and B, but you could very well go from FS average to atlas A and from FS average to atlas B.
But then can I go from, like, is it possible to connect from one atlas to another? Or-
Well, yes, in a sense, because like if you have one specific source point, let's say it has the coordinates -4 + 8, 12, that is defined in your atlas A and in your atlas B. You just need to know what this one source point corresponds to in your individual brain, which will be slightly different formed and have a different coordinate system. So once you are in this normalized brain space, the points are defined in many different atlases. And I think different toolboxes will have a different number of those atlases available for you. Okay. Other question? I think there.
I have two questions that are quite recurring, I think. We hear these over and over. The one is about the way the rank of the data influences the whole source computation, source estimation, and in particular, the rank of the noise covariance matrix, and therefore of the data that is used to compute the noise covariance matrix. Can you say a few words about the effect that removing SSP components or ICA components has on that, and whether the same SSP components or ICA components or even the max filter correction needs to be applied to the noise covariance and to the data of the data of interest?
Okay. So we've seen this morning what it looks like when data is rank deficient, and I've explained that this is a problem. In my tutorial, we actually looked at how our beamformer completely fails on the data we had if we do not take measures to take into account that our data is severely rank deficient. So we found out that, for example, we still had to regularize, even though we whitened the data and used a truncated inverse to begin with, which are all three measures to address that problem. So that as a background of that you really need to take care of this. If you're lucky, you get an error message. If you're unlucky, you just get garbage out. Now, I also got this question this morning in the hands-on, should I do ICA on the data at all then, which I hear is one of the concerns you shared. You can replace ICA in this sentence with signal space projection as well, or in an extreme case with max filtering. There is no cutoff. I got asked that, how much can I be rank deficient and it's still okay? There is no such cutoff. I think if you remove one or two components in an ICA or an SSP, that is not usually a huge problem. We can really deal with that by regularizing or truncating or whitening. And for example, whitening would be done on the data, on the forward model, and on the covariance matrix. Usually the algorithm will take care of that for you. However, this morning also gave this hunch that if you know that you want to go to source reconstruction, especially if you want to use a beamformer, where this is especially important because the data covariance plays such a huge role in constructing that filter, you should think of that from the start of your experiment, and maybe not just max filter because you can, but really think, do I need it? So don't just apply everything you can to your data because it's fun or because it's available, but really think it through and be as sparse with those methods as you can. If, of course, your data is horrible without max filtering, you will have to take care of that step and then see if you can fix it in the source reconstruction step for the beamformer, or if that's not possible, minimum norm is more forgiving for that. So then you could use that instead. I'm not sure if there was another mini question in your question that I'm forgetting about.
No, that it answers it nicely.
Okay, good.
It's yeah, it's a regular question, I think. And another one that we also got this morning was about the opportunity to merge EEG, MEEG channels in estimating the sources.
Yes. So what you can see, for example, if you look at the data of EEG and MEEG, or also of radiometers and magnetometers, with just one glimpse at the y-axis, is that they have different orders of magnitude. And that, of course, influences source reconstruction. So if you would reconstruct sources using magnetometers and radiometers, the magnetometers wouldn't play that much of a role because I think it's 3 orders of magnitudes. Those values are smaller or something like this. So you need to bring them onto the same level. There's different approaches to do that. I can speak to M&E Python. Here we solve this by using whitening. So if you supply more than one channel type, the beamformer algorithm will complain if you do not also supply a noise covariance matrix, which would be used to whiten the data, which would, among other things, bring them onto the same level. Another thing the algorithm does under the hood is, if you imagine the covariance matrix across channels, you could get the covariance matrix of radiometers with magnetometers. That's something we kick out, but that's nothing you have to take care of. That's all taken care of under the hood. So shorter answer, it's possible, but you have to make sure that you get the sensors onto the same level so that they both play a role. What it does not address, though, I have gotten that question before in other contexts. This does not take into account the different sensitivity profiles of magnetometers and radiometers, where magnetometers can see deeper, only implicitly through the data, but it's not modeled in the source reconstruction.
So is it worth the burden of, and that's perhaps another part of the question, basically. Is there enough to be gained from exploiting these different types of data to then have to struggle with so many questions, basically? Yeah,
I would say in M&E Python, it's really easy. You just compute your noise covariance as you computed your data covariance, but do it on for example, the baseline, and the rest is taken care of for you. So then it's really not much of a hassle. It's maybe a bit different if you look at EEG and MEEG, where you already, during the experimentation stage, have to do way more work, right? You have to put on the EEG cap and all of that. Maybe depending on your systems, your data will be way noisier. So I think there you have more trade-offs. But for radiometers and magnetometers, if the algorithm permits it to easily use both, I think that's a good way to go.
I may have a question. I'm taking the opportunity of having you two here because it goes a little bit beyond the source reconstruction. It's in between testing significance and source reconstruction, you mentioned, Rita, this morning that we could either reconstruct source with leaving unconstrained orientation of the dipoles on distributed surface, or you can constrain. In one case, the constraint, you have one time series, and in the unconstrained, you have 3 time series per vertices.
Yeah.
And I wonder if you have strategies to test significance between participant or source localization in the case in which you have the 3 orientations. Because, well, one way to represent is to show the power, but then how to test differences.
Yeah, so what MEEG would do is combine the 3 orientations using, I think, a root mean square. Another way to do it is to run a PCA or so on the 3 orientations, which then more or less gives you out the optimal orientation again. So you more or less approach the same as you would do with a scalar beamformer just through the back door. I have never thought about whether you could test all 3 orientations separately and whether that would make sense, especially across participants. Maybe.
I think it's not. It's probably not something that you're experimentally controlling, and it's given the different cortical folding over participants. I don't expect it to be very consistent, so that's why we often do not plot the orientation in individual participants, because it's going to be different anyway. But the second strategy that you described, like using a PCA, or which you can compute using a singular value decomposition, that is a very common strategy, because then you don't lose the sign.
Yeah.
Which is, in a way, is very nice, because you can still see positive and negative deflections that you can compare across conditions within the same participants, having the same orientation, which can also be annoying because the sign can be arbitrary, and the same way as the sign of a independent component analysis can be arbitrary. So if you want to plot this over space, like if you want to plot this on neighboring vertices on your cortical grid, you can have a very patchy representation. So there's a little bit of trickery is needed to make sure that the sign of neighboring vertices is consistent, such that you have consistent activation.
Thank you very much. Are there any other questions? Okay. Well, then I think we're gonna thank again Rita. Thanks, Robert.
And Robert.